Hi, and welcome to this video where we'll look at how to solve ODEs and IDEs, ordinary differential equations and integral differential equations. These equations are often accompanied by initial conditions, like for example, you have your ODE here, and you know that at time 0, x is equal to 1, and x dot at time 0 is equal to 0.5. So we'll be focusing on such problems. Also, I should say we're focusing on linear ODEs and IDEs. We'll solve these equations using the Laplace transform. A key property we'll be using is this over here. When you apply the Laplace transform to the derivative of a function f, then the derivative disappears. If you like, when you have a derivative here, it becomes multiplication by s. The Laplace of f prime is s times the Laplace of f minus the function f at time 0. And there are no derivatives here. This is theorem 419 in the textbook. Overall, the idea is that you take your ODE, which lives in the time domain, you apply the Laplace transform, you move over to the s domain, and there you have a simple algebraic equation, which then you can apply the inverse Laplace transform and get your solution, if that's what you want. So here is a simple first example. I have written the property I just showed you again here, so we don't have to scroll up. The ODE is x plus 2x dot is e to the minus t, and we know that x at time 0 is equal to 1. Let's apply the Laplace transform. I'm using the notation big X to mean the Laplace transform of little x. So take this equation, the Laplace of little x is, just written Laplace of little x, plus twice the Laplace of x dot is the Laplace of e to the minus t. Let's start from the right hand side. We know that the Laplace of e to the minus t is 1 over s plus 1. This I'm writing as big X. And for this, that's the key part, is that I'm using the property I just showed you. So Laplace of x dot is s times big X minus x at 0 plus. And you might be noticing a little discrepancy here. In the equation, we have x at 0 plus. In the problem statement, we have x at 0. Now, the thing is, this is an ODE. Unless you have anything very, very weird, meaning unless you have any Dirac deltas, we'll talk about this later. So unless you have any deltas here, you can be quite sure that x is continuous. So x at 0 plus and x at 0 are the same thing. So this now is equal to 1 because of this. And moving things around, doing now some simple algebraic manipulations, after all we have an algebraic equation, we can work out what x is. X is this. It happens to be a rational function, polynomial divided by a polynomial. Now, if you very much like, you can take the inverse Laplace transform and obtain a solution in the time domain. More about this in a next video. In this first example, we looked at a differential equation that had x dot. What if you have x double dot? What if you have higher order derivatives? The good news is that you can apply the same principles. We gave this property. Laplace of f dot is s times Laplace of f minus f at 0 plus. Alright, now you can substitute f equals g prime, g derivative with respect to time, and you can obtain a formula for the Laplace of g double prime, which is s times the Laplace of g prime minus g prime at 0 plus. And the good news is that we know what this is from before. It is s times, and then you have s times Laplace of g minus g at 0 plus. And outside you have minus g derivative at 0 plus. You can do the multiplications there. You can denote the Laplace of little g by big G. And that's it. That's your formula for the Laplace of g double prime. And this begs the question, what about the Laplace of g triple prime, fourth derivative, fourth order derivative, and so on? I'll just leave this to you as an exercise, or you can check in the textbook, there is a formula. Let's have a look at another example where we have indeed a second order derivative. We have x double dot. you have this differential equation now, and I'm giving you these initial conditions. Same as before, we'll define big X to be the Laplace of X, and we'll go ahead and apply the Laplace transform. The Laplace of little x is big X, and then we have plus 0.1. The Laplace of x dot is given by this formula. And then we have plus 2 times, and we'll apply the Laplace to x double dot. It is s squared times x minus s times x at 0 plus minus x dot at 0 plus. And dropping the pluses, x at 0 plus means limit as time goes to 0 from the right hand side. Because we are assuming x is continuous. It is indeed continuous because we don't have any deltas here. It is a very ordinary differential equation. So this is 1, this is 0, and this is an algebraic equation. There is nothing weird about it. We're moving terms around, we're collecting the x's, and we end up with x equals 1 over s. We've been very lucky here, because it's a very simple formula, and in fact we can recognize that this is the Laplace transform of 1. In the time domain, it's the function 1. Well, as you saw before in the previous example, not always is it like this, and that's why we need the inverse Laplace transform. That's what we did actually, just in this case the inverse Laplace was really obvious. Let's have a look at this general picture again. We have an ODE, we apply the Laplace transform, and we end up with an algebraic equation. As we'll see in the next video, the process of taking the inverse Laplace transform is a little bit tedious. But sometimes we don't even need a solution. Sometimes we're asking different questions. For example, is my solution oscillatory? Does my solution settle at a given value? Does it go to 0? Does it go to 1 at infinity? What is the initial slope of my solution? So all these questions can be answered, thankfully, without having to determine the entire formula, if you like, of the solution. We can determine properties easily. Here are 3 properties we can obtain in a very easy manner. One is to tell what the limit of x is at infinity, if a limit exists anyway. The second property is to tell what the initial value of x is, and the third one is to tell what the initial slope of the function is, that is x dot at 0 plus. So I can determine very easily x at infinity, x at 0 plus, and x dot at 0 plus. And more properties actually, but we'll come back to this. Enter the initial value theorem. The initial value theorem is a very simple formula that gives you x at 0 plus. It is the limit as s goes to infinity of s times x of s. Now remember, s is a complex number. In this limit, we're taking s to be a real number. We're writing s goes to infinity over the real numbers. This is the initial value theorem, and it is theorem 428 in the textbook. Here's a quick example. Suppose someone has taken an ODE, they somehow derived it from physics, let's say, and they applied the Laplace transform, and they have given you this expression. This is like the solution in the S domain. And the question is, what is x at time 0 plus? Well, x at 0 plus is the limit as s goes to infinity of s times x of s. And we can tell very quickly that this is equal to 2. How can we do this? There is this little property of limits which you can show very easily. It says that the limit as s goes to infinity of a polynomial of degree n over another polynomial of degree n is just a over b, the coefficients of the highest order terms. But be careful here, it has to be the same order. Here we have order 2, s squared over order 2. And we have 2s squared divided by 1s squared. 2 over 1 is 2, and that's it. Now, if you want to prove this property, all you have to do is divide both parts of the quotient here by 1 over s to the power n. You do times 1 over s to the power n, and I'll leave this to you as an exercise. So with this theorem, with the initial value theorem, we can determine x at 0 plus. But we can use also the same theorem to determine x dot at 0 plus. The initial value theorem says that x at 0 plus is the limit as s goes to infinity of s times the Laplace of little x. Well, let's take this formula and apply it to x dot. Then we have x dot at 0 plus is the limit as s goes to infinity of s times the Laplace of x dot. And we know this is s times x minus x at 0 plus. Time for an example. Someone has taken an ODE, they applied the Laplace transform, and they have ended up with this expression for big X. The question is, what is the initial slope? First of all, let's determine x at 0 plus. X at 0 plus is this limit. Substitute, well, this s and this s cancel out, and you end up with 0. Right, this was the first step. Second step, x dot at 0 plus is the limit as s goes to infinity, s times the Laplace of x dot, which is this. And you have this, actually, let me better write this down. This we said already is 0. We found out here. So it is s squared times x. And this turns out to be 1 over 3, using the same rule for rational functions. So that's it. We can determine the initial value and the initial slope. We can determine the initial curvature as well, if you like. We can determine x double dot at 0 plus. Now, let's move on to the final value. We talked about the initial value, the final value now. The final value theorem, I'll skip to the formula. The formula looks like this. X at infinity is limit as s goes to 0 now of s times x at s. But the thing is that the final value theorem comes with some very important terms and conditions. And you cannot apply it always. You can only apply it if these conditions are satisfied. So x is a rational function, polynomial over polynomial, times an exponential function. This exponential function in the Laplace domain pertains to a delay in the time domain. P and Q are polynomials, and these are the important bits. The poles of x are the roots of the polynomial q. The roots of the polynomial q have a negative real part. You can have one possible exception. You can have a single pole at 0. For this to make sense, I've put here a few examples. So function number 1, 1 over s. The question is, what are the poles, and can we apply the final value theorem? So 1 over s, you have a single pole at 0. Can we apply the final value theorem? Yes, we can. Second function, 1 over s plus 1 times s plus 2. What are the poles? They are minus 1 and minus 2. Can we apply the final value theorem? Yes, absolutely, we can. Function number 3, we have q. This is q, the denominator. It is of order 3 plus 1 equals 4. So there must be 4 roots of this polynomial. That is 4 poles. You have clearly minus 1. But this minus 1 is a triple pole. We'll denote it like this. Triple pole. And you have another pole, because of this, at plus 1. At plus 1. Yes, you have one pole with a positive real part. So you cannot apply the final value theorem in this case. What about this case over here? 2 over s squared plus 1. S squared plus 1 is the important part. The roots are plus and minus j. Plus j and minus j. Can we apply the final value theorem? Let's scroll up. It says no poles with a non-negative real part. So these have a negative real part. No, these have a zero real part. Do these fall under the exception? There is one exception. One single pole at zero. No, these are not at zero. So you cannot apply the final value theorem in this case. One more example. You have this s plus 1 squared plus 2 squared. The poles here are minus 1 plus minus 2j. And the minus 1 came from here, the real part. The 2j came from here, the imaginary part. That's really a convenient way to write a polynomial that has complex conjugate poles. So this is minus 1, this is plus 2, this is minus 2. So you have one pole here and one pole here. Are these okay? These have a negative real part. So yes, these are fine. You can apply the final value theorem. And the last one is this polynomial. You have here a pole at 0, but it is double. You have a pole at minus 5, you have a pole at minus 6. So you have one at minus 5, you have one at minus 6, and you have one at 0, which is double. Can you apply the final value theorem? No, because the pole at 0 is double. You can apply it if it's single, not in this case. And let's have a look at this example. Someone has taken an ODE, they have applied the Laplace transform, and they have ended up with this big X. The question is, what is X at infinity? So before rushing into just taking the formula and substituting in what we have, we need to tell whether we can apply the final value theorem. The poles of X are, you see here, 0 and minus 1, which is triple. That's fine. We have a single pole at 0. That's fine, okay? So yes, we can apply the final value theorem. And X at infinity is the limit as s goes to 0 of s times big X. And you can say this is 1 over 8. One last thing. We talked about ordinary differential equations, but with this approach we can also tackle integral differential equations where you have integrals. You know the property for the derivative where you have multiplication by s. Now when it comes to integrals, we have this property where the Laplace of an integral from 0 to time t is 1 over s times the Laplace of x. And you might be wondering, what is the Laplace of the integral from some time, let's call it a, of x of tau d tau, where a is not necessarily 0. Well, that's a good exercise. You can definitely work this out very easily. Let's have a look at an example where we have an integral differential equation. Say 2x plus this integral equals e to the minus 3t. Now this can be, for example, an RC circuit where this is the where you have a voltage V, which is e to the minus 3t. You have a current X, and this is the voltage drop across the resistor, and this one is for the capacitor. So you can end up with an equation like this. Now take the Laplace transform, 2x becomes 2 big X, the integral becomes 1 over s times x, and e to the minus 3t, take the Laplace transform, and you have this. This is already an algebraic equation, no derivatives here, and you can very easily solve for x, and you end up with this. And now you want to find out the final current, let's say x at time infinity. Can we apply the final value theorem? Let's see what the poles are. You have a pole at poles. You have one at minus 1/2. You have another one at minus 3. Both of these are okay. So yes, we can apply the final value theorem, and x at infinity is the limit as s goes to 0 of s times your function x, and you can see that the limit is equal to 0. So thank you very much for watching, and see you next time.